Hi, hello there. Welcome to Number Systems. Guess what? This is a 32-bit IPv4 address of a computer in a network. So this is 1100.1010.1010.0000.1010. It is shown in binary format. This is the IPv4 address for the same computer in dotted decimal 192.168.10.10. Which one would you rather work with? IPv6 addresses are 128 bits. To make these addresses more manageable, IPv6 uses a hexadecimal system of 0 to 9 and letters A to F. As network administrator, you must know how to convert binary addresses into dotted decimal and dotted decimal, into binary. You will also need to know how to convert dotted decimal into hexadecimal and vice versa. You still need your binary conversion skills to make this work. Surprisingly, it is not that hard when you learn a few tricks. So why wait? Let's get it on. This video lecture is entitled Number Systems. At the end of this video lecture, you should be able to calculate numbers between decimal, binary, and hexadecimal systems. Subtopics are divided into two sections. You've got binary number systems, which has the objective of calculating numbers between decimal and binary systems. And the second part is the hexadecimal number system. So the objective would be, at the end of this module, specifically the hexadecimal number system, you should be able to calculate numbers between decimal and hexadecimal systems. Binary number system. IPv4 addresses begin as binary, a series of ones and zeros called bits. These are difficult to manage, so network administrator must convert them into a decimal. This topic shows a few ways to do this. Binary is a numbering system that consists of digits, zeros, and ones called bits, as mentioned earlier. In contrast, the decimal numbering system consists of 10 digits, consisting of digits 0 to 9. Binary is important to us to understand because hosts, servers, and network devices uses binary addressing. Specifically, they use binary IPv4 addresses, so as shown in this diagram here. So these are represented IPv4 addresses in binary. So each address consists of a string of 32 bits. So this would be 8 bits for every octets. So your IPv4 addresses has 4 octets. 4 octets having 8 bits each. So therefore, it is 32 bits. Now each address, as mentioned, is a string of 32 bits divided into 4 sections called octets. So each octet contains 8 bits or 1 byte separated with dot. For example, PC1 in the figure has been assigned an IP address 192.168.10.10. So basically, this one here is a representation in binary, while the figure here on the right is a representation in decimal or dotted decimal. All right. So this is the binary equivalent of 192.168.10.10, and 192.168.10.1 here is represented on this 32 bits string. All right. Now, for solid understanding, of the network addressing, it is necessary to know binary addressing and gain practical skills converting them between binary and dotted decimal IPv4 addresses. This section will cover how to convert between base 2 or binary and base 10 decimal number systems. Binary positional notation. Learning to convert binary to decimal requires an understanding of positional notation. Positional notation means that a digit represents different values depending on the position the digit occupies in the sequence of numbers. You already know the most common numbering system, the decimal or base 10 notation system. The decimal positional notation operates as described on this table here. So let us describe each of the following on this table. Let's start with row 1, radix. Radix is the number base. Decimal notation is based on 10. Therefore, the radix is 10. Row 2, position in number, considers the position of the decimal number starting with from right to left. So that would be 0, 1, 2, and 3 on each position. These numbers also represent the exponential value to calculate the positional value in the fourth row. So row 3 here calculates the positional value by taking the radix and raising it to the exponential value of the position in row 2. So take note that n0 is equals to 1. So that's why we have here 10 raised to 0 is 1, assuming that n are the positional or position in number here. Okay? Now, row 4 positional value represent units of thousands, hundreds, tens, and ones. To use the positional system, match a given number to each positional value. The example in the table in here illustrates how positional notation is used with the decimal number 1234 or 1234. Okay, so if you are given, for instance, this 1234 here or 1234 positional value, so we need to calculate it. Okay, so something like for thousands, you've got 1, that's 1 times 1000, and that would give you 1000. Okay, so the second digit is 2, so that would be 2 times 100. Okay, so that would give you 200. All right, and then the third value, which is 3, the position is 10, so 3 times 10, that would give you 30. And the last one would be 4 times the positional, which is 1, so that would be 4. Now adding all of this, 1000 plus 200 plus 30 plus 4 would yield to 1234. Binary positional notation. So in contrast, the binary positional notation operates as described in this table here. Okay, so the following table here, okay, so describe each row of the table. Let's start with the radix. Radix is the number base. So binary notation is based on 2. So therefore, the radix would be 2. Row 2, position in number, considers the position of the binary number starting with from right to left. So that would be, okay, so 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so same thing with what we did with the previous slide on decimal. We just have to raise the radix to the position in number. So that would yield 2 raised to 0, 2 raised to 1, 2 raised to 2, until 2 raised to 7. And the positional value would be 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to 4 is 16, 2 raised to 5 is 32, 2 raised to 6 is 64, and 2 raised to 7 is 128. All right. Now, the example in this table illustrates how binary 11000000 corresponds to the number 192 here. So if the binary number have been 10101000, then the corresponding decimal number would be 168. Now, how did we get 192 from here? Now, using the positional value that we have here, okay, so we've got 128, 64, 32, 16, 8, 4, 2, 1. So this is basically 8 bits, okay? And then the number or binary number would be 1111000000. So to calculate, we just have to multiply the binary number to its positional value here. So that would give you 1 times 128 is 128. Okay? And then this is also 1. So that would be 1 times 64. That would give you 64. 0 times 32 is of course 0. So any number multiplied to 0 would yield to 0. Now we just have to add those numbers. Okay? 128 plus 64, that would yield to 192. So therefore, to convert 11000000, that would yield to 192. Or simply, we just have to add all the positional value here, having a binary number of 1. And this is 128 plus 64 would yield to 192. Convert binary to decimal. So to convert a binary IPv4 address to its dotted decimal equivalent, we just have to divide the IPv4 address into 4 8-bit octets. So next, we need to apply the binary positional value to the first octet binary number and calculate accordingly. So for example, so we've got here 11000000. So we all know from the earlier discussion that this would yield to 192 here. All right. Okay, so for the second octet, say that would be 10, 10, 10, 0, 0. So we just have to plot it on the positional value. Okay. And then we need to add all those ones there. So we've got 3 ones. So that would be 128. Okay. Plus 32 here. And then plus 8. And that would yield to 168. Okay, so convert the third octet. Say that would be 4 zeros here and then 1011. Okay, so we just have to plot it on our positional values here. So that would be 4 zeros and then you've got 1011. So we just have to add those values having ones here, and that corresponds to 8 plus 2 plus 1, and that would yield to 11. All right. And for instance, the last octet would be 40 10 10 as shown in the table. Okay, so plot it on the positional value again. So we've got 10 10 here, so that would be 8. All right. And then 1 here corresponds to 2. 8 plus 2, that would yield to 10. So this completes the IP address and produces 192.168.11.10. Decimal to binary conversion. So it is also necessary to understand how to convert a dotted decimal IPv4 address to binary. So a useful tool is the binary positional value table. So like what we have used in the recent slides, you've got 128, 64, 32, 16, 8, 4, 2, 1 here. So basically, this came from 2 raised to 1, 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to 4 is 16, 2 raised to 5 is 32, 2 raised to 6 is 64, and 2 raised to 7 is 128. All right. Now, Is the decimal number of the octet n equal or greater than the most significant bit 128 in our example here? Okay, if no, then enter the binary 0 in the positional value of 128. So simple as that. Okay, and then if yes, then add a binary 1 in the 128 positional value and subtract 128 from the decimal number. Okay? Next, is the decimal number of the octet n equal to or greater than the next most significant bit, this time 64? If no, then enter binary 0 in the 64 positional value. If yes, then add a binary 1 on this location here, okay, and subtract 64 from the decimal number. Okay, so that's how the algorithm works. Let's move on to 32. Is the decimal number of the octet n equal to or greater than the next most significant bit, which is 32? If no, then enter binary 0 in the 32 positional value. Okay, if yes, then add binary 1 in the 32 positional value and subtract 32 from the decimal number. Okay, same thing with 16. Is the decimal number of the octet n equal to or greater than the next most significant bit, which is 16? If no, then enter binary 0 in the 16 positional value. Okay, if yes, then add binary 1 in the positional value and subtract 16 from the decimal number. Okay, so same thing with 8. Is the decimal number of octet n equal to or greater than the next most significant bit, which is 8? If no, then enter 0 in the 8 positional value. If yes, then enter or add binary 1 in the 8 positional value and subtract 8 from the decimal number. Now for 4, is the decimal number of the octet n equal to or greater than the next most significant bit, which is 4? If no, enter binary 0 in the 4 positional value. Well, if yes, add 1 or binary 1 in the positional value of 4 and subtract 4 from the decimal number. Okay, so next would be 2. If the decimal number of the octet n is equal to or greater than the next most significant bit, which in this case is 2, if no, then enter 0 in the 2 positional value. Okay, else if yes, add binary 1 in the 2 positional value and subtract 2 from the decimal number. Okay, and the last one, same thing with the previous one. Is the decimal number of the octet n equal to or greater than the last most significant bit, 1? If no, add 0 in the 1 positional value. If yes, add binary 1 in the positional value of 1 and subtract 1 from the last decimal number. So that's how the algorithm works on converting decimal to binary. Okay? Now, to help you understand the process, let us consider 192.168.11.10. Okay? The first octet is 192, is converted to binary using the previously explained positional notation process. Now, it is possible to bypass the process of subtraction with easier or smaller decimal numbers. For instance, notice that it is fairly easy to calculate the third octet converted to binary number without actually going through subtraction process. 8 plus 2 equals 10. Okay? Now, the binary value of the third octet is 401010. Okay? And that would be 8 plus 2 plus 1. Okay? So, which is 11. Alright? Now, the binary value of the fourth octet is 00001011. Converting between binary and decimal may seem challenging at first, but with practice, it should become easier over time. All right? Okay, so IPv4 addresses. As mentioned in the beginning of this topic, routers and computers only understand binary, while humans work in decimal. It is important for you to gain thorough understanding of these two numbering systems and how they are used in networking. Now, what you can see here on the figure is a dotted decimal address. Dotted decimal address 192.168.10.10. Now, in the figure, this is what you call octet. This address is made up of 4 different octets. All right, so 192 is equivalent to this first octet having a binary value of 11000000. All right, now what you can see here on this diagram is a 32-bit address. The 32-bit address, the computer stores this address as the entire 32-bit data stream. Okay, so if you have 192.168.10.10, you represented that in binary using these values here. Hexadecimal number system. Now you know how to convert binary to decimal and decimal to binary. You need that skill to understand IPv4 addressing in your network. But you are just as likely to be using IPv6 addresses in your network. To understand IPv6 addresses, you must be able to convert hexadecimal to decimal and vice versa. Just as decimal is a base 10 number system, hexadecimal is a base 16 system. The base 16 number system uses digits from 0 to 9 and letters A to F. Okay, now the figure here shows the equivalent of decimal and hexadecimal values from binary 0000, which is equivalent to 0 in decimal, and 1111, which is equivalent to 15 in decimal, and F in hexadecimal. Okay, so take note that from numbers or decimal 0 to 9, okay, so you'll have this representation here. Okay, so to get 9, of course, this is 8421 from the positional values presented earlier. So 8 plus 1 is 9. Okay, now this is 1010. So using the positional values 8421, this would yield to 10. And 10 in decimal is, of course, decimal is 10. And in hexadecimal, that's equivalent to A. So after 9, the next is A. All right. So if we are going to count this in hexadecimal, so that would be from 0 to 9. Okay, so once you reach 9, next is A, B, C, D, E, F. The next to F is 10. So hexadecimal 10 is not equivalent to 10 in decimal. All right. That's equivalent already to 16 in decimal. Okay? Binary and hexadecimal work well together because it is easier to express a value as a single hexadecimal digit than as 4 binary bits. Okay? Now, the hexadecimal numbering system is used in network to represent IPv6 addresses and Ethernet MAC address. Now, IPv6 addresses are 128 bits, okay, in length, and every 4 bits is represented here by a single hexadecimal digit. So for a total of 32 hexadecimal values here. Okay, so that would be counting from 0000 to FFFF. All right, or that would be from 0000 to 1111, which is equivalent to F. So this would be F, 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 getting this value here. Okay? Now, IPv6 addresses are not case sensitive, and it can be written in either lowercase or uppercase. Now, as shown in the figure here, the preferred format for writing an IPv6 address is this one. So x colon 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 x. Okay? Now, with each x consisting of 4 hexadecimal values. When referring to 8 bits of an IPv4 address, we use the term octet. In IPv6, a hextet is the unofficial term used to refer to segments of 16 bits or 4 hexadecimal values. Now, each x here is a single hextet, 16 bits or 4 hexadecimal digits. Decimal to hexadecimal conversion. Converting decimal numbers to hexadecimal values is straightforward. So we just have to follow the following steps. First, convert the decimal number to 8-bit binary strings. And then, divide the binary strings in groups of 4 starting from the rightmost position. Convert each 4 binary numbers into their equivalent hexadecimal digit. The example provides the steps for converting 168 to hexadecimal. So for example, 168 converted into hex using this 3-step process. So first, 168 in binary is equivalent to 10101000. Again, using the positional values we've got here, all right, 1, 2, 4, 8, 16, okay, 64, or 32, 64, and 128. So adding that 128 plus 32 plus 8, that would give you 168. All right, so 128 plus 32 is 160. Plus 8 here is 168. Alright, so that is using this first step here. Alright, so the next one is we need to group, okay, this binary here into 2 groups. Okay, each group having, of course, 4 bits. So something like 1010, alright, you've got this one here, and then 1000 is the 1000 marked in red here. Okay, so the next thing is we need to convert each of the 4 binary numbers into their equivalent hexadecimal digit. Okay, so 1010 is equivalent to 10. Okay, so how do we get 10? So this is 8, 4, 2. So 8 plus 2 is 10. And the equivalent of 1010 is hex A. Okay, and then 1000, this is equivalent to hex 8. So therefore, 168 is A8 in hexadecimal. Hexadecimal to decimal conversions. Converting hexadecimal numbers to decimal values is also straightforward. Follow the steps listed. First, convert the hexadecimal number to 4-bit binary strings. Second, create an 8-bit binary grouping starting from the rightmost position. Third, convert each 8-bit binary grouping into their equivalent decimal digit. So for example, D2 needs to be converted into decimal using these 3 steps provided here. So let's start with the first step, okay, so which is D2 for instance. So D2 in 4-bit binary string is equivalent to 1101 and 0010. Now, how did we get 1101 here? Okay, so from the positional values, okay, presented in the previous slide, So take note that we have here 8, 4, 2, 1. So that would be 8 plus 4 is 12 plus 1 is 13. And 13 decimal is equivalent to D in hexadecimal. That's why you've got D here equivalent to 1101. All right. Now, how did we get 2? Or how did we get 0010 for 2? So take note that again, via positional values here, this would be 8, 4, 2, 1. You've got 1 on 2, so that would be 2. Okay? And then this 1101 here and 0010. Okay, so we just have to append these two values. So 1101 and 0010 is an 8-bit grouping. Okay, so we just have to group these two 4 bits here, forming an 8-bit value. So afterwards, let us convert this binary here, which is 11010010 in decimal. So again, by placing here 128, 64, 32, 16, 8, 4, 2, 1. Okay? So adding 128 plus 64 plus 16 plus 2 here would yield to 210. Alright, so therefore, D2 is equivalent to 210 in decimal. Alright? You might want to see the video demo on these number systems after this theoretical discussion. Thank you very much for watching and listening. Have a great day.